Hey guys, here's the spiral review for spiral 4. We're going to look at some functions and domain stuff first, which sounds really fun to me. First off, we've got the function y is equal to the square root of x plus 3 plus 5. And what you're being asked to do here is to talk about three different people's explanations of the domain, which means you're going to have to find the domain yourself. There are two things going on here as far as finding domain. The first is that you're going to have some expectation of being able to do this algebraically. And the second is that you're going to have some kind of expectation of being able to do this graphically. Domain algebraically is not too bad. We're looking at, oh good, I'm in highlighter mode apparently. Y is equal to the square root of x plus 3 plus 5. And go back to pen. And what we know about square roots is that we can't have negative numbers on the inside and still get them to show up on a graph. So for the domain algebraically, what we're going to do is to take the square root of x plus 3 and just the inside part and say that has to be greater than or equal to 0. When I do this out, that means that the domain is going to be x is greater than or equal to negative 3, or going from negative 3, should be a square bracket there, like I drew at infinity. Let's not do that. So going from negative 3 to infinity. Okay, so Mr. Regis has a domain is okay. Miss Coggeshall has sort of a range that's okay, but her brackets are kind of messy. Butterworth just is not okay because his domain doesn't even match up with what you got algebraically. The second way to approach is to think about this graphically. And here, we're given the mother function down below. We've got the square root of x plus 3 and the square root, and then plus 5 on the outside. That means each one is going to go 3 to the right. And then up 5. So if we go 3 to the right, 1, 2, 3, up 5, my first point would be there. 3 to the right, up 5. And then 3 to the right, up 5. 1, 2, 3. There we go. Which means my new graph would look something like this. The domain based on this looks similar to what I have here, so negative 3 to infinity, because we're just going to start at negative 3 and keep going. And the range would be from 5 to infinity, because we're starting at 5 and going up. So Miss Coggeshall definitely has the right range. The domain's a little bit wonky, but not quite, right? All real numbers is not right for Mr. Regis. This is a function because we're talking about something that's passing the vertical line test, so that's okay. And then after all that, we're okay. We've talked about why both Mr. Regis and Mr. Butterworth are full of baloney. We talked about the domain algebraically, and that's by setting this thing up. You need to know how to do that. And we talked about the domain algebraically. By algebraically, the second time I mean graphically. Ooh, function operations involving a graph. Woohoo! I am a little bit sad that you guys don't get to see the colors on your spiral review sheets, but we have them here, so that makes it lots of fun. Looking at function operations, we know that we need to find some of these values based on this graph. Okay, so this graph is f of x, I also have an equation for g. Oh, that's sneaky of me. So I give you a graph and an equation this time. Cool. F of 3 means the height of f at x equals 3. Okay, so x equals 3 is here. This appears to have a height of 0. So f of 3, because that's the point 3 comma 0, is equal to 0. G of negative 3 means I'm going to plug in negative 3 to my equation g of x. Negative 3 squared minus 8. Negative 3 squared is 9, times 3 is 27, minus 8 is going to be 19. All right, f minus g of 2. Really important for you to know, this does not mean that we're multiplying f of something and g of something by 2. That was a really common mistake I saw in the last spiral. We've got to go f of 2 minus g of 2. When I plug this in, f of 2, in other words, the height of the graph, f of 2, so we're looking at 1, and then g of 2, I'm going to plug that in here. 3 times 2 squared minus 8. All right. That's going to be 12 minus 8 is 4. So 1 minus 4 is going to be negative 3. Awesome. F of g of 1. First I've got to find g of 1. And that's equal to 3 times 1 squared minus 8, which is going to be negative 5. I'm still seeing people trying to multiply here instead of taking this and plugging it in. So f of g of 1 is the same thing as saying f of negative 5. Okay, here's the rub. If I look at my graph, negative 5 is over here. My graph doesn't exist. So f of negative 5 does not exist. I'm going to use D and E because I don't have any room. For those of you that go on to take calculus next year, you'll also use D and E a lot for things that do not exist. Last piece, all values of k such that f of k equals 0.5. Oh boy, that's different. So we might look at the first thing is, okay, this is the height of the graph. So height of f at x equals k is 0.5. And that kind of gives it away a little bit. So 0.5 is here, and it looks like I've got two places that have a height of 0.5. It looks like k could be, and that's, I don't know, 1.5-ish. And k could also be 2.5-ish. You thought we were done, but we're continuing. I'm going to sketch a graph. Ooh, that's exciting. And it's the same thing that we were using in the function section. How crazy is that? So we're going to sketch this graph. I realize one may have gone a little bit crazy there. I'm going to use my transformation notation, and I'm going to take a look at this. I'm going to go point by point to see where each of these points are going to end up. All right, so that's negative 3, negative 3. We've got negative 1, negative 1. We've got 0, negative 1. We've got 2, 1. And we've got 3, 0. Okay. I'm going to start with 2 times f of x minus 1 plus 2 is equal to my new function. Okay. I know that I'm going to take the inside here, and I'm going to set that equal to each x value. So let's start with negative 3, negative 3. I'm going to take that first negative 3, and that's equal to x minus 1. Therefore, my new x value is going to be negative 2. Okay. For the y value, I'm having two things happening. I'm going to multiply by 2 for the number out front, and then I'm going to add 2. So if I start at negative 3, I'm going to multiply that by 2 for the number out front, and then I'm going to add 2. 2 times negative 3 is going to be negative 6, plus 2 is negative 4, and that's my first y value. So negative 3 comma 3 is going to become the point negative 2 comma negative 4. and change colors. Okay, I'm going to use some of the space on the next page to continue this. So negative 1, negative 1. First thing, x minus 1 is equal to negative 1. That means that x is equal to 0. And then I'm going to multiply the other negative 1 times 2 and then add 2. And that's going to give me 0. Cool, so my second point is going to become 0, 0. And that's that first segment. Okay, it actually might be a little bit more effective to use red to show that that's replacing the red segment. My next point is going to be 0, negative 1. 0 equals x minus 1. That means that x equals 1. And then I'm going to take negative 1 times 2 plus 2, and I get 0 as an answer. So we're looking at the point 1, comma 0. And I'm going to use my blue because, well, that's the blue section. Next up, we're looking at the point 2, comma 1. And I'm going to do x minus 1 is equal to 2. In other words, x equals 3. And then y times 2 plus 2 should be 4. That's the point 3, comma 4. Okay. 3, comma 4 is up here. And then finally, I'm going to look at the point 3, comma 0. And 3, comma 0, I'm going to do the same thing. X minus 1 is equal to 3. That means that x equals 4. And then I've got 0 times 2 plus 2 is 2. So 4, comma 2. So keeping those in line with the colors, the description here might be all points moved right 1. Then we multiplied y by 2. And then we went up 2. Cool. All right, m of negative 2 and m of 4. There are a couple different ways that I could do this. The first way that I might be able to do this is to take a look at my graph. M of negative 2, so the drawn-in graph is m. Negative 2, m has a height of negative 4. M of negative 2 is negative 4. M of 4, I'm going to find the height there. M of 4 is 2. As an alternative, let's say you didn't know how to graph this thing. I could just plug that in. So m of negative 2, I could write as 2 f of negative 2 minus 1, and then plus 2. Okay, in doing that, sorry for running over the next lines, so in other words, that's 2f of negative 3 plus 2. F of negative 3, okay, that's going to be negative 3. So 2 times negative 3 plus 2. 2 times negative 3 is negative 6, plus 2 is negative 4. You can plug these in instead of graphing them if you have trouble graphing them. Okay, next up we've got some charming polynomial problems. I'm going to start with a graph. And we're trying to find a graph for, an equation for this polynomial. And there are a couple things that I would like to remember as we kind of go through this. And that's what the shapes of graphs look like based on a few things. The first is going to be end behavior. This graph is going up and to the right and down and to the left. Opposite directions means we're talking about an odd polynomial with a positive leading coefficient because I'm going up and to the right. So this could be like something x cubed or something x to the 7th. It's got to have an odd degree, and it's going to be going with a positive leading coefficient. That's important. Second part of this we need to know our multiplicities of zeros. A zero that looks like this is caused by something cubed. A zero that's going straight through is caused by, wow, this is getting worse and worse for writing, something that doesn't have an exponent unless it's a 1. And a bounce is usually caused by a squared. It's actually any even exponent will create some kind of a bounce. But I might then take a look at the degree of different pieces of this, and it looks like I've got a pass through here and a pass through there. I would say the degree in both of those places is probably 1. That means that we're looking at x plus 3. We're looking at x minus, well, I'm sorry, that's x minus 0, I guess, or just x. Okay. Next up, I might take a look at any bounces I have. And it looks like I've got a bounce at positive 1. And what a bounce is going to do is going to be some kind of a squared or other even exponent. So x minus 1 squared could work there. And then finally, I've got one other type of thing going on, and that's at negative 7, and that's kind of a hesitation as I pass through there. That looks like my cubic value. I'm going to put that out front just because I'm out of room. And we get x plus 7, and that's going to be at least cubed. And just to make sure, I've got 1, 2, 3, 4, 5, 6, 7. 7 total x's. A degree 7 makes sense because this has to be an odd degree. I'm going to talk about the frozen turducken next, just because that seems to be next on my line of sight, although it's not necessarily the next problem, depending on how you look at this. So it's thrown straight up, and the height of this might end up looking something like this as it goes up and comes back down. H of t, okay, that's the current height. V sub 0 is the initial upward velocity, okay, so that's here, and that's that number. H sub 0 represents the initial height of 0.75 meters, okay. Find the maximum height of the turducken. I want to think vertex, and we have a shortcut to find the vertex that could be useful for us in this problem. So I'm going to start by rewriting my equation with the stuff involved. So we've got h of t is equal to negative 4.9 t squared plus v sub 0, which is 25 t plus 0.75. Okay, we said that the, zoom in way further. The vertex, we're looking at an x value of negative b over 2a. And that can help us find the vertex pretty quickly. So in this case, we're talking about negative 25 over, and then I'm going to look at negative 4.9. So negative 4.9 times 2 is going to be negative 9.8. Okay, when I divide those, so 25 divided by 9.8, we get a time of 2.55 seconds. Okay, it asks for the maximum height. For the maximum height, I'm going to plug this in to h of t. So h of 2.55. So that's going to be negative 4.9 times 2.55 squared plus 25 times 2.55 plus 0.75. And I get a height of 32.64 meters. That's a really high-flying turducken. Okay, when does this hit the ground? This is definitely the type of problem that the quadratic formula was created for, because these numbers are really not pleasant. So we're looking at negative 25 over negative 9.8, that's what we just figured out, plus or minus the square root of 25 squared minus 4 times negative 4.9 times 0.75, and that's all over negative 9.8. So when we do this out, we get that 2.55 number, and we got 25 squared minus 4 times negative 4.9 times, I almost screwed that up in my calculator, times 0.75, which is 639.7. I'm going to take the square root of that. So it's this plus 25.29 divided by negative 9.8. Should be plus or minus there. So divide by 9.8. We get 2.58. I'm going to add 2.55 to that, and we get a time of 5.13. The other time would be just about 0, and that would be when it's about to leave the ground, or actually a little bit before it leaves the ground. But this t equals 5.13 is definitely when the turducken will go kersplat. Okay, and then we've got the other problem, which really isn't the last one, which is about weather radar with a circular region with a 200-mile radius. So we're talking about a circle with the radius is 200. I like us to remind ourselves that the area is equal to pi r squared. No, they're not. They're round. Ha 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 ha. That's a great joke. I'm so glad that my split personality told it. So in this case, the area would be pi times 200 squared. And if I were to do that, because I'm being very lazy, we get the area is 125,663.7 square miles. Okay, so we're going to increase the area by a certain amount. In other words, the radius is now going to be 200 plus x is equal to the radius. So then the area would be pi times 200 plus x squared. For the third part, if we're talking about 125,600 is equal to pi times 200 plus x squared, what we might do is to take this piece by piece. So I might divide by pi, so 125,600 divide by 3.1415926. When I do that, I get 39 2,979.72 is equal to 200 plus x squared. If I take the square root of both sides, I end up with 199.95 is equal to 200 plus x. We're only going to deal with the positive version because the negative version doesn't make a lot of sense in this context, but that could be an answer here too. And because I chose such good numbers, you find out that your update increased it by negative 0.05 miles because you're a terrible engineer. So yours actually decreases it for however much money they spent on you. Woo! We've got to solve a pair of right triangles. I'm going to start off by using some trig. Okay, I know if I've got this angle, we're looking for the other angle, so that's 90. So we're looking at 180 in total. I've got 90 left to use. Minus 33 is going to be 57 degrees. Okay, to find x, I might use sine of 33, and that's equal to 21 over x. I'm going to multiply both sides by x, and I end up with x sine 33 is equal to 21. And if I divide both sides by sine 33, I end up with x is equal to 21 over sine 33, which is going to end up somewhere around 42. Okay, looking at my other value, I could use the Pythagorean theorem for that. It means I might as well find that trig value. So we're looking at 21 divided by sine 33. That's going to be 38.55. So if I want to use Pythagorean theorem, 21 squared, I'm going to call that z, because I like z, plus z squared is equal to 38.55 squared. So 38.55 squared, 1486, minus 21 squared, 1045. Z squared equals 1045.1025. Do some square rooting. I get z is 32.32. I've got x, I've got z, I've got all the angles. I have solved the triangle. The other one, I'm looking at 18 and 9. Cool. I don't know this angle. I don't know this other side. I might start for the other side. I'm going to call this W. So I've got W squared plus 9 squared is equal to 18 squared. And if I do that out, I've got W squared is equal to 324 minus 81. 324 minus 81 is going to be 243. 243. Square root both sides. And I get W as the square root of 243, which you might recognize as 3 times 81, which is kind of neat, because 3 times 81, if I square root that, I'm going to go up here, sorry, the square root of 3 multiplied by 9. 9 square roots of 3. If you didn't feel that creative, that's fine. You could leave that as either the square root of 243, or if you really wanted to, 15.58. Okay, let's set this up. So we're looking for, I don't know, I know these two are already here, so that's opposite, hypotenuse compared to this question mark. Sine question mark is equal to 9 over 18, which is a half. Hey, that looks kind of familiar to some angles we've been working with the past few days. But that's okay. So to get an angle from a ratio, I have to use the inverse sine. This is something that we're still having trouble with that we need to fix. So sine inverse of a half is going to be 30 degrees. What? How crazy is that? This is the 30, 60, 90 right triangle. Because if that's 30, that's got to be 60. We've got 4a. The sun is at an angle of elevation. All right, here's my sun. Angle of elevation, that's going to be here, 58 degrees. A tree, there's my tree. Cast a shadow. Okay, so shadow is going to be down here, 20 meters long. How tall is the tree? So shadow is the length in the bottom. The tree is what I don't know. That's opposite and adjacent. So we're looking at tangent. So tangent of 58 is equal to x over 20. X is equal to 20 multiplied by tangent of 58. And you can call it done there. Or if you want, you can do it out. 20 times tangent of 58. X equals 32. And it's pretty close to 32 even. So 32 feet tall is the tree. Person starts out 17 miles from the base of a tall mountain. Ooh, that's exciting. There's my mountain. It's really tall because it's just a peak. All right, 17 miles. And they look up at a 4-degree angle of elevation. All right, when they move 12 miles closer, so now if they're 12 miles closer, that means they're 5 miles away. What is their new angle of elevation? Oh, this is cool. This is like a 2-part problem. How awesome is that? So if I were to do this, I might try to do the purple triangle first. And then, once I have the purple triangle, I might take a look at this other guy, because that's going to be the same height in both cases. How amazing is that? So first things first, what I could do is treat this as a tangent problem. So we've got tangent of 4 is equal to x over 17. 17 tangent of 4 is equal to x. So 17 tangent 4, and that's going to be 1.18. That seems really small. Oh, wait, we're in miles. That's fine. So 1.189 miles. Okay, that's the same one. And now I'm trying to find that angle. That looks like a tangent again. So tangent of question mark is equal to 1.189 over 5. That means that tangent inverse of 1.189 over 5 is equal to whatever that question mark is. Tangent inverse 1.189 divided by 5, and I get 13.37 degrees. All right, one last doobie. This is law of cosines. I know I'm solving for an angle. I'm using A. So I'll probably use my A setup. A squared is equal to B squared plus C squared minus 2BC cosine of A. Plugging things in. A, that's C, and that's B. 4 squared is equal to 10 squared plus 8 squared minus 2 times 10 times 8 times cosine of A. 16 is equal to 100 plus 64 minus 160 cosine A. Here's where the most common thing to go wrong is. You cannot combine this with the numbers. That's got to stay separate. That's 164 out front. Get a minus 164 to both sides. Negative 148 is equal to negative 160. Cosine of A. Now I'm going to divide by 160 negative to get rid of that. And that's 0.925 is equal to cosine A. I know I have to use inverse cosine to get A. So inverse cosine of 0.925, and that's equal to 22.33 degrees.